Welcome back to Singularity, the channel where we explore the extremes of the cosmos, from the tiniest quantum ripples to the most massive stellar beasts in the universe. Today, we're diving into the story of a cosmic titan, the heaviest star ever discovered. What's its name? Where is it? How far away is it from Earth? How bright is it? And how much hydrogen does it burn every single second? What happens when a star this massive dies? And finally, what kind of black hole will it leave behind? Let's explore the life, the future, and the final fate of this heavyweight champion of the universe. So what is the heaviest star ever found? That title currently belongs to R136A1, a true monster among stars. This isn't your average stellar giant. This is a hypergiant located in the Tarantula Nebula, which lies inside the Large Magellanic Cloud, a satellite galaxy of the Milky Way. It's about 160,000 light-years away from Earth. Now, what makes R136A1 so incredible is its sheer mass. While our Sun weighs in at 1 solar mass, that's the standard unit for measuring stellar mass, R136A1 was originally estimated to have started its life at a staggering 320 solar masses. Even after shedding a considerable amount of mass through intense stellar winds and radiation, it's still estimated to weigh over 200 solar masses today. And when it comes to brightness, R136A1 is a blinding beacon in the universe. It shines with a luminosity nearly 9 million times greater than the Sun. That means if you replaced our Sun with R136A1, Earth would be fried instantly, and even Pluto would become a scorching wasteland. It's so bright that even though it's 160,000 light-years away, astronomers can still study it from here on Earth. So how does it fuel such an outrageous energy output? Like most stars, R136A1 burns hydrogen into helium through nuclear fusion. But the scale is, honestly, unimaginable. Our Sun converts about 600 million tons of hydrogen into helium every second. R136A1? Estimates suggest it burns through more than 100 times that amount every second. Over 60 billion tons of hydrogen. Every second. That's equivalent to burning the entire mass of Mount Everest in hydrogen. Every few seconds. But there's a catch. The bigger the star, the shorter its life. All that power comes at a cost, a rapidly ticking cosmic clock. R136A1 is a very young star by cosmic standards. It's estimated to be only 1 to 2 million years old. Just a baby compared to our 4.6 billion-year-old Sun. But unlike the Sun, which will live for about 10 billion years in total, R136A1 will probably last no more than 2 to 3 million years. That means this monster of a star is already burning through the final stages of its life. We may be witnessing R136A1 just before its ultimate death, a spectacular explosion that will light up the skies of its galaxy. So what happens when a star like R136A1 dies? Well, it won't go quietly. It's destined to go supernova, or maybe even beyond that, into what's called a pair-instability supernova. That's actually a rare and extremely powerful explosion caused when the star's core gets so hot that gamma rays spontaneously turn into electron-positron pairs, which weakens the internal pressure and leads to a catastrophic collapse. In a typical supernova, that core collapse usually creates a neutron star or a black hole. But in a pair-instability supernova, the explosion can be so violent that it tears the star completely apart, leaving no remnant behind at all. However, if enough mass manages to survive, it could still collapse into one of the most massive stellar black holes ever formed. R136A1 is right at the edge of this limit. It may explode and vanish entirely, or it might leave behind a black hole of over 100 solar masses, an object so dense that not even light can escape its gravity. Now let's talk a bit about how bright this supernova would actually be. If R136A1 goes supernova, or even hypernova, it could be, honestly, billions of times brighter than the Sun for a short period of time. It would outshine an entire galaxy, if only for a few weeks. Just for comparison, the famous SN 1987A, which also happened in the Large Magellanic Cloud, was visible to the naked eye from Earth, and it was only a fraction as powerful as R136A1's explosion is expected to be. R136A1's death would be visible from Earth with even modest telescopes, despite being located 160,000 light-years away. And although we wouldn't be in any danger, it would be a cosmic event unlike anything humanity has ever witnessed in real time. But what if a star like R136A1 were, closer to us? Would we be in danger? Yes, absolutely. If R136A1 were within 10,000 light-years of Earth and its death triggered a gamma-ray burst, and if the beam were pointed directly at us, the Earth's atmosphere could be stripped of its ozone layer, exposing the surface to deadly ultraviolet radiation from the sun. It could even lead to mass extinctions. Thankfully, R136A1 is way too far to pose any real threat. At 160,000 light-years away, it's safely outside the cosmic danger zone. Still, the explosion itself will be a once-in-a-millennium spectacle for astronomers. It will mark the final act of one of the universe's most extreme stars. If R136A1 leaves behind a black hole, and not all of its mass is blown away, we're looking at a stellar black hole of truly unprecedented proportions. Most stellar black holes we've detected so far weigh between 5 and 20 solar masses. But this one could be over 100 solar masses, placing it in the elusive category of intermediate mass black holes, the missing link between stellar mass and supermassive black holes. We know supermassive black holes, like the one at the center of our Milky Way, weigh millions or even billions of times the mass of the Sun. But how do you get from a 10 solar mass black hole to a billion solar mass black hole? Stars like R136A1 might be the answer. Now you might wonder, have we ever sent a probe to study R136A1 up close? The answer is no, and probably never will, at least not with current technology. At 160,000 light-years away, R136A1 is far beyond the reach of any spacecraft we can build. Even traveling at the speed of light, it would take 160,000 years to get there. What we do have, though, are incredibly powerful space telescopes, like the Hubble Space Telescope and the James Webb Space Telescope, which allow us to peer deep into space and study stars like R136A1 in exquisite detail, using light that began its journey long before humans ever walked the Earth. It's a sobering thought. Every image we take of R136A1 is also a look 160,000 years into the past. So why study stars like R136A1? Because they hold the keys to understanding the early universe. Massive stars like this were more common in the early cosmos, forming in dense stellar nurseries and seeding the universe with heavy elements through their violent deaths. Without them, there would be no oxygen, no carbon, no iron or gold, and no planets, no life, and well, no us. By studying R136A1, we're not just watching a giant star. We're witnessing the kind of stellar furnace that made our own existence possible. R136A1 is a cosmic titan, a star so massive, so bright, and so short-lived, it defies much of what we thought we knew about how stars work. It burns through more hydrogen in 1 second than the sun does in an hour, and it's racing toward a death that will shake its galaxy to the core. And in its death, it might give birth to one of the most massive black holes we've ever seen. Stars like this push the limits of physics, challenge our understanding of stellar evolution, and give us a front-row seat to the life cycles of the most extreme objects in the universe. If you found today's deep dive into R136A1 fascinating, let us know in the comments, and tell us what you'd like us to explore next. Should we talk about the coldest star, the fastest spinning neutron star, or maybe dive into what happens inside a quark star? Your suggestions fuel this channel. And if you haven't already, Please hit that subscribe button, give this video a like, and turn on notifications so you won't miss our next journey through space, time, and everything in between. Thanks for watching Singularity, where we chase the wonders of the universe one question at a time. Until next time, stay curious.